Hi, this is Mrs. Hanson. I'm one of the chemistry teachers here at the high school, and I'm going to share with you some information about intermolecular forces. This stuff is super important, so you need to take really good notes, and when you go to class, your teacher's going to expect you to sort of understand what's going on, and you can apply it in the lab. The great thing about this video is that you can stop it, you can rewind it, you can listen to it again, so make sure and take advantage of that. All right, let's get started. So we're going to review a little bit the difference between intermolecular forces and intramolecular forces. Remember, intermolecular forces, or IMFs as we call them, are attractive forces between different molecules. So when we look at the sample of water molecules, we are not talking about the actual covalent bonds. Those are intramolecular forces, but rather we're talking about the attractive forces between one molecule and another molecule. It's usually represented with this dotted line. The stronger the intermolecular forces holding molecules together, the stickier the molecules. It's like magnets. So this water molecule is sort of sticky to this water molecule. The strength of that stickiness is what IMFs are all about. The stickiness factor can cause a lot of physical properties, one of which is boiling point. So let's talk about boiling point. Boiling point is the amount of energy needed to make something turn into a gas. So if a substance has a high boiling point, then it takes a lot of energy to turn it into a gas. It takes a lot of energy to turn into a gas, then why is that? Well, one molecule must be really strongly attracted or really sticky with the other molecule. Therefore, the substance must be strongly held together, which means what kind of IMFs? High intermolecular forces. Okay? So, there are some different types of intermolecular forces. There's three that we're going to learn about. The first one is called dispersion forces, or sometimes called London forces. A dispersion force is typically the weakest of the three forces we're going to learn about. And basically the way it works is that you have electrons, right? Well, in any particular atom, let's say this is a normal atom, the electrons, those are little dots, are sort of evenly distributed. But at any one moment, the electrons sort of get to one side. Well, now you have this electron shift. This creates a dipole. Remember, a dipole is when you have a distinct positive end versus a negative end. When all the electrons are sort of on one side, that's going to create this negative end. Well, this temporary dipole is going to cause a dipole in other neighboring molecules. So you get sort of this effect, that this temporary dipole was created, and then this negative end attracts the positive end, or the nucleus, basically, in another molecule, and you create this dipole. Well, if this continues through the whole entire sample, you're creating this really weak attractive force. That is what a dispersion force is. Okay, so if you read through this, it's a weak force that results in a molecule or an atom's electrons shifting to one side, okay, creating a temporary dipole. The dipole can cause or induce a dipole in other nearby atoms and molecules. These dipoles attract, just like a weak pair of magnets. So again and again, we're going to come back to this idea that IMFs are sort of like magnetic attractions between molecules. Okay? So that's your dispersion force. All right. Here's really important piece of information. All molecules have dispersion forces. Okay? It's just whether they're stronger or weaker. Okay? The strength of a dispersion force is all going to be based on how well those electrons can get shifted to one side or the other. So here's my question for you. What sort of atoms do you think would be most easily polarized? Polarized is just another word for the electrons getting shifted to one side versus the other. Do you think choice A, atoms with lots of electrons, so like big atoms or big molecules, or choice B, atoms with few electrons, so small guys? Well, I hope you think about it. And if you said atoms or molecules with lots of electrons, you would be right. More electrons equals more electrons getting shifted to one side, which creates a stronger dipole. Okay, so that's going to be a stronger dispersion force. Okay, so here's a little challenge for you. Example 1. Circle the molecule with the highest boiling point. Explain your choice. So right now you should pause and you should try this question. Okay, so go ahead and pause. Make sure you pause. Okay, so now I'm going to continue. I hope that you went through this problem and that you picked octane. Why did you pick octane? Well, you know what? It's a bigger molecule. C8H18, it has more atoms, so that means more electrons, so it has more opportunity to be polarized or for the electrons to shift to one side or the other, okay? So the more electrons, the bigger the molecule, the greater the dispersion force, okay? Now, all molecules and atoms have electrons, so all molecules and atoms have dispersion forces. However, dispersion forces are the only intermolecular force that affects nonpolar molecules and noble gases, okay? So that means there's some other intermolecular forces we need to talk about, okay? So how about dipole-dipole forces? Now, dipole-dipole, they're slightly stronger. A dipole-dipole force is a medium strength magnetic attractive force between two polar molecules. So for instance, if you looked at HCl, so you got H bonded to chlorine, okay? And as you talked about earlier, the chlorine is going to have that partial negative charge because it's more electronegative. It's going to pull on the electrons more, and that's going to leave hydrogen with a partial positive charge. Okay, that is a polar molecule. It distinctly has a negative end and a positive end. Well, this molecule will very easily attract the positive end of another molecule. Okay, and so on and so forth. All right, so that's how a bunch of polar molecules would be attracted to each other. Remember, the dotted line in the middle, that is the intermolecular force, or in this case, a dipole-dipole force, okay? So it's a little bit stronger than dispersion because it's an actual polar molecule, whereas in dispersion, it's just sort of the electrons shifting to one side versus the other, okay? So keep in mind that any substance that has dipole-dipole, that's a polar molecule, also has dispersion forces, okay? But since dipole and dipole forces are stronger, it's going to be more significant than the dispersion forces, okay? All right, the last one. You guys are doing great. Hydrogen bonding, or H bonding. You guys may have learned about this in biology. The great thing about hydrogen bonding is it's not bonding, okay? It is actually just an especially strong type of dipole-dipole force, okay? And it always is going to occur between the hydrogen in a really polar bond, such as an NH, OH, or FH bond, and the O, N, and H atom of another molecule, okay? So how does this work? Well, water illustrates hydrogen bonding. So if you take oxygen bonded to hydrogen, this right here is a normal covalent bond, but it's really polar because oxygen is it's one of the most electronegative elements on the periodic table. Okay, and hydrogen has a pretty low electronegativity, so there's a really big electronegativity difference between these two atoms. That creates a really polar bond. So therefore, it's kind of like just having a stronger magnet. So the O of one molecule will attract the H of another molecule. Okay, and it's because of the strength of this polar bond that the attraction between the O here and the H here, this attraction right there, the hydrogen bond, is actually stronger than most normal dipole-dipole attractions. Okay? So really, it's the exact same thing as dipole-dipole. The only difference is that it only occurs when you have, I call it the fun, almost like fun, trio. Fluorine bonded to hydrogen, oxygen bonded to hydrogen, or nitrogen bonded to hydrogen. If you see that in a molecule, then that molecule can exhibit hydrogen bonding. Okay? So why? Let's summarize. What factors cause hydrogen bonding to be such a strong dipole-dipole force? Okay, well, the one is the one we just mentioned. The large electronegativity. It's got like 800 syllables. The large electronegativity difference between H and O and H and F and H and N. So that creates a really, really, really polar bond. And then the other factor is the small size of H, O, N, and F. They're really small, so what that means is that they can get close to each other. And when they can get close, that means that the strength is just going to be all that much greater, okay? So those are the reasons why hydrogen bonding is just an especially strong dipole-dipole. All right, so let's see. What are some applications of this hydrogen bonding business? Well, because it's an especially strong attractive force, it has a pretty dramatic effect on physical properties, okay? This graph right here. I know it's a little bit hard to read, but on this side, this is boiling point. Okay, that's boiling point. And this is the molecular mass, or the weight, or how big the molecule is. Okay? Now this blue line, this is what you would normally expect. Okay? This is going down family 4 on the periodic table. So it starts with carbon, bonded to 4 hydrogens. And then it goes to silicon, bonded to 4 hydrogens, and so on and so forth down the family. Well, CH4 is the smallest of the molecules, has the least mass. So, you know what? It has pretty low dispersion force. So you'd expect it to have a lower boiling point, okay? It doesn't have strong attractive forces, so it doesn't take as much energy to turn into a gas. And then more dispersion forces, so the boiling point's a little higher, okay? And then the boiling point just keeps increasing. But these other lines don't follow that trend. The reason is because of hydrogen bonding. If you look right here, this is the next family, which is nitrogen's family. So this is family 5 on the periodic table. So this is NH3, and then you got PH3, and then ASH3, so you're going down the family. Well, you'd expect NH3, because it has the smallest mass, you'd expect it to be like down here, kind of following the same trend as this guy. But because of the hydrogen bonding, that's why you see this weird blip. Okay, the NH3 is way up here. It has an especially strong or high boiling point because it's got this especially strong attractive forces. You see the same thing with the next family. This is the family 17, the halogens, HF. It's got that hydrogen bonding thing going for it, so it's got especially strong attractive forces for its small size. And then here's water all the way up here, whereas this is like H2S, H2SE. These are the other members of the family that oxygen's in, but H2O has especially strong attractive forces because of the hydrogen bonding. Okay, so that's something your teacher will definitely talk about, okay? So to summarize, normally we would expect the intermolecular forces to increase going down a family because of size, so that means because of dispersion forces. Okay, because of increasing dispersion forces. However, hydrogen bonding is an unusually strong force, and it leads to surprisingly high boiling points. All right, so I hope that's clear. Hydrogen bonding is definitely the trickiest of the intermolecular forces. Finally, this one's not really an IMF because IMF stands for intermolecular force. Okay, and these aren't about molecules, but it's called an ion-ion force. This is the easiest one of all of them. It's the electrostatic or magnetic attraction between ions. So a cation, which has a positive charge, positive, right, like a cat, positive, and an anion, which has a negative charge. Okay, it's in an extreme dipole because it's literally a positive ion attracted to a negative. Okay, so it's like dipole on steroids. It's very strong, stronger than dipole or even hydrogen bonding. You know what? An ion-ion force, you actually know all about it because it's better known as an ionic bond. Therefore, what's one of the properties of ionic compounds? Well, they're all solids at room temperature. They all have super high boiling points because you'd have to put in a lot of energy to actually break that positive to negative ion attraction. All right, well, guess what? The rest is up to you. There's some practice problems, and your teacher will give you a deadline. I want you to use the notes and use the information you learned to give those practice problems your best effort, okay? And if you have questions, I'm sure you can ask your teacher. Thanks a lot for listening. I appreciate it. If you look at the bottom of your practice problems on the next page, there is some other resources you can look at online and maybe in your book if you still need some more help understanding this. Thanks a lot. Bye.